This video is about trigonometric equations and their inverse functions. Just a reminder about inverse functions, we can think of inverse functions as undoing the original function. Algebraically, that means if we compose a function with its inverse, then they should quote-unquote cancel away and we'll be left with x. So f of f inverse of x equals f inverse of f of x equals just x. Notationally, we use this superscript of -1 right here and right here to indicate an inverse function. This is not to be confused with the exponent of -1 that indicates a reciprocal. So the inverse function is not the same as a reciprocal function. So just a quick example of that, if we have cosine inverse of x, our superscript here of -1 will be right next to the cosine, so that's going to indicate our inverse. However, if we have cosine x and then a -1 out here on the on the outside, you can think of it, that's going to indicate our reciprocal, which is 1 over cosine of x, which is actually the same as our secant function. So it's really important that you don't confuse these two different meanings for the superscript here. So in one case it indicates an inverse, and then in the other case it indicates the reciprocal. In terms of points, if I take an x and I plug it into my function f, I get out a y. So what the inverse does is I can plug in that y and it tells me what my original x is. So that means if I have a point x, y on the graph of my original function f, that point is going to correspond to the point y, x in the graph of my inverse function. If we're comparing the graph of a function with its inverse function, they're the same except for one of them is the reflection over the line y equals x. And this happens simply because of this previous relationship where we've basically just taken the coordinates and switched them. So graphically that's how we'll see it, as a reflection over the line y equals x. Let's take a look at the graph of cosine. So I want you to notice that from left to right, our inputs go on forever in both directions. So that means that the domain of our cosine is infinite. So it's from -infinity to +infinity. And it's also really important to kind of understand that the things that we plug into cosine are angles. Now I want to come back to this graph, and this maximum here we know is at 1, and then this minimum is at y equals -1. So the range of our regular cosine function is from -1 to 1. So I just want to remind you that the outputs for my cosine function, remember, are x coordinates of a point determined by the angle. So we input an angle and we get out an x coordinate. So that's what the cosine function does. So our cosine, we plug in an angle, we get out an x coordinate. We can plug in any angle from -infinity to +infinity, and the x coordinate we get out is going to be between -1 and 1. So intuitively, if we talk about the inverse of the cosine function, the things that we're going to get out of the function are going to be our angles, and the things that we plug in are going to be our x coordinates. So these have kind of switched roles. So now we're going to plug in an x coordinate to go backwards and figure out what the angle was. Now I just kind of want to remind you that when we talked about arc length, the arc length was the same as our angle measure in radians. So when we use this term arc cosine, it means the arc of the thing whose cosine is whatever a given x coordinate. So that's where that arc cosine comes from, because it's telling you the arc is a number. So that's kind of a good way to remember that the things that we are getting out are actually our angles. So the same goes for arc sine or arc tangent. So the arc part is telling us that the thing we're getting out is going to be the angle. So that's why it's a really useful notation. So let's say we take our cosine graph and we switch all of our inputs and outputs. That's the same as reflecting the graph over the line y equals x. The graph we get looks something like this. Now this is not actually the graph of arc cosine. So this is the graph that represents kind of the inverse of the graph of cosine if we were to just simply reflect it and leave it. However, we're looking for the inverse function. So in order to be a function, the graph that we're looking at has to pass the vertical line test. And as you can see, this thing that I have graphed here does not pass the vertical line test, so it's not a function. So we need to do something to take care of that. So basically what I want to do is restrict this graph so that I've only got one cycle. By doing this, it ensures that it's going to pass the vertical line test. So you may be wondering why I chose to keep this portion of the graph, and I'm going to explain that to you using the cosine graph. When we look at our cosine graph, the most intuitive way to identify one cycle is usually to start at the line y equals x and go to pi. So that's exactly, the line x equals 0, or the y-axis, up to pi. So if we just say, show me one cycle of cosine, this would be the graph that you would be most likely to present to me. Or I guess it would be all the way to here. So we want the first half of that. So we want to cut it off so we don't get this part where it goes back up and kind of repeats all these values, because we want to be able to have a one-to-one inverse function. So I'm going to cut it off there, and I'm just going to use this portion. So that is the portion of our graph that we use to determine the graph for our cosine function. So I want you to notice that the domain for this little segment is from 0 to pi, while the range of this segment is from 0 to pi. Similarly, the domain is from -1 to 1 for the cosine for this segment, and the domain here is from -1 to 1 for our cosine. So we've just restricted the values that we're working with to ensure that we've got an actual function here. So based on this graph, we can go ahead and fill out our domain and range for our arc cosine function. So the domain is going to be from -1 to 1, and our range is going to be from 0 to pi. So because of the way we've kind of defined the cosine inverse function, the arc cosine function, if you plug it into your calculator, so you plug in some x-coordinate, it's always going to give you out the angle between 0 and pi. So visually, on our unit circle, that means that all of the angles we're going to get out are going to be in the first half of our circle right here. That's just one limitation that I really want you to be aware of when you're working with our inverse functions. So we can follow a very similar line of logic to construct the inverse function for our sine function based on the graph. So here, once again, our values go from +1, to -1 at the bottom. So our range for our sine function is -1 to 1. And just like with the cosine function, our domain is -infinity to +infinity. So it doesn't matter what angle we plug into our sine function, we'll get values between -1 and 1. So if we kind of trace off one cycle of our sine function, we can get all the way from 0 to 2 pi. So that's how we would just kind of naturally mark off a cycle. However, just like we looked at the unit circle briefly here to kind of see what was going on, in order to avoid the ambiguous case that we had between 0 and pi when we did the law of sines, you may remember it was ambiguous because we weren't sure which angle exactly it was talking about. So when we restrict our sine function, when we're converting, or when we're looking for, I guess, our inverse function, we restrict it differently than what might be intuitive. So for the sine function, if we want to have an entirely unambiguous inverse, if we define it from -pi/2 to +pi/2, then we're going to avoid that ambiguous case like we had with the law of sines. So that's actually what I'm gonna do. So this is where we restrict our sine domain, and we come up with the graph for arcsine. So notice my range here is from -pi/2 to pi/2, and this is -1 to positive 1. This graph does indeed pass the vertical line test, so it's a function, so we can go ahead and define its domain and range. So a really fine point about the range here, notice I used the regular parentheses, meaning those endpoints are non-inclusive. That was actually incorrect. I was checking the wrong part of my notes. So right here, our endpoints are included because we don't run into any trouble with our vertical line test. The last graph that I want to look at in detail is the graph of the tangent function. So just kind of looking at the graph, it looks like it's going to make sense to cut it off from pi over 2, or negative pi over 2 to positive pi over 2, because that's going to, it appears like it's going to give us an inverse that makes sense. A couple of properties of the original tangent function that I want to remind you about. Our domain is everything except for odd multiples of pi over 2. So I'm just going to fill that in there. Our domain is, I'm just going to write it as not odd multiples of pi over 2. And then when we switch over to kind of talking about our inverse, it's going to make sense to use this division because then we won't have to accommodate those asymptotes. And we can see clearly from the graph here that our range is from negative infinity to positive infinity. So I can fill that in as well. This is the graph of arctangent. So remember that arc means that the thing that we're getting out is an angle. It's the same as the arc length. So just a key way to keep track of those. So I said it would make sense to restrict from negative pi over 2 to pi over 2, and that's exactly what I've got shown here. This clearly passes the vertical line test, so we're good to go. The range is between negative pi over 2 and pi over 2. However, here is where we don't have those endpoints included because those are actually asymptotes. We never touch those. So when we write the range for our arctangent function, we need to write it using regular parentheses. So we go from negative pi over 2 to positive pi over 2. And then our domain, as you can see, is everything. It goes from negative infinity to positive infinity. It doesn't matter. So going back to our unit circle here, our range are any of these angles. So it makes sense that we can plug in any number from negative infinity to positive infinity, because remember, our tangent function we could think of as being the slope of the terminal side of our angle. So that goes everywhere from negative infinity, where it's like super negative, and then it's like a little bit negative, and then it's 0, and then... So no matter which number we plug in as being the slope there, we can get one definite angle out. So it makes sense that we can plug in anything into the arctangent and get one specific angle out of the arctangent function. With our knowledge of the graphs of cosecant, secant, and cotangent that we talked about in the last video, we could then, if we were so inclined, construct the graphs of the arcsecant, the arccosecant, and arccotangent functions, and then also determine the domain and range of those. So for their time's sake, if you want to, now would be a good time to pause and go maybe find those graphs on your old notes or look them over, and then I'm just going to go ahead and give you those values for the domain and range. Now I just want to do an example to kind of show you what you might be doing for practice later. So I've got written here cosine inverse of sine of cotangent inverse of root 3 over 1. So remember, when we compose functions, we have to start from the inside out. So that's what I'm going to do. So starting from the inside out, the first thing I need to address is this cotangent inverse of root 3 over 1. So because it's cotangent inverse, I know that the thing on the inside there is a value. So that means that my answer is going to have to be an angle for this part. So I know that cotangent of some angle equals root 3 over 1. I also happen to know that cotangent equals 1 over tangent. So the tangent of some angle is 1 over root 3. Well, tangent, I know, is defined as sine theta over cosine theta. So I get 1 over root 3 when my sine equals 1/2 and my cosine equals root 3 over 2. Just like this. And that happens on my unit circle at the angle pi over 3. Sorry, I had that backwards. So my cosine here is my x, and my sine is my 1/2. So it's pi over 6. Right here is my angle. So for the very inside part, I have cotangent inverse of root 3 over 1. So for that part, I get that my theta equals pi over 6. So I can literally just substitute in pi over 6 right here. So now I'm looking for sine of pi over 6. Well, sine of pi over 6 is something that we know. It's this y-coordinate here, so it's 1/2. So, since the sine of pi over 6 is 1/2, I can substitute that in then. And now I'm looking for the cosine inverse of 1/2. So when my cosine of theta equals 1/2, what is my theta? Well, that happens at theta equals pi over 6. And therefore, pi over 3, just like I have drawn in this diagram over here. So our final answer there is pi over 3. I'd really encourage you to take a couple minutes and make sure you really understand what's going on here. So I started out with this original problem, cosine inverse of sine of cotangent inverse of root 3 over 1. So my first step was to find cotangent inverse of root 3 over 1, which I did by reducing the problem to an easier problem. So I just took a bunch of steps to kind of make it simpler, so I got closer and closer to something that I already know. So I started by rewriting this cotangent inverse as an equation where I have cotangent equals root 3 over 1, because those two statements are equivalent. And then I recognized that my cotangent equals 1 over tangent, so that what I was actually looking for was an angle where the tangent equals 1 over root 3. Well, by definition, the tangent function is sine over cosine, which means that in order for my tangent to be 1 over root 3, my sine has to be 1/2 and my cosine has to be root 3 over 2. And that only happens at the angle pi over 6. So once I determined that my angle for the very inside part, this right here, was pi over 6, I can substitute that in. So I can think of getting rid of all of this and just replacing it with pi over 6. So once I do that, then I'm just finding sine of pi over 6, because remember we're working from the inside out. The sine of pi over 6 was 1/2. So once again, substitution. I can think of all of this as being gone, and that I'm just looking for cosine inverse of 1/2. Well, the angle that gives me a cosine equal to 1/2 is the angle pi over 3. So that's my final answer. That's the thing I was looking for. So it really could happen where you have something like this, where you're going back and forth between inverses and regular functions. So you really need to keep track of the thing that you're looking for, whether or not it's a value or an angle. So just be careful and make sure you write out your work and your steps, so you can keep track of what's going on, and then that way it'll also be easier for me to kind of check your work and make sure that you're on the right page.